So we'll start off to look at the angular kinematics variables, these guys, but now we promote them to vector form, okay? So why do we even want to do that? It's because these guys were vectors, right? The linear kinematics variables were vectors. So these guys should also tell us something about the direction, right? So how do we make them a vector form? If I make them a vector, they'll have, this is a slightly abstract question in some sense, because this I kind of understand. The velocity, it's just describing, right, the speed of this object in this direction, like 5 meters per second in this direction. And then, yeah, I need to describe directions with three pieces of information, namely an axis and an angle, and which way it goes, something like that. Yeah, but it's very easy to visualize. But this is how much radians per second. What direction is there to talk about? And how can we even define, like, what do you mean by rotating in the northward direction? This is where we need to become, we need to be a bit smart. And there's some very creative people who came up with a way to describe directions, even with rotations, right? Let me tell you what I mean is, let's say this is the plane, the XY plane, right? XY plane like this. And you're rotating like this. If I ask you, well, I know what can you describe the direction of this rotation? The best you can do is say something like this is counterclockwise, right? Or this way is clockwise. Can I define a vector for it, right? Okay, so this is angular velocity. I was kind of sloppy with the words angular speed and angular velocity, but now let me make it formal, right? Before it didn't really matter. I wasn't really talking about the vector version of it. But now let's be formal. So angular velocity. So what is the magnitude? All I need to do is be clever and define what is the magnitude and the direction, and then I will have a rigorous definition of this guy, right? The magnitude is easy, right? The magnitude is just what we had before, right? For example, we said the tangential speed, if we want to relate it to the linear one, is this times r, right? Everything, just take the Greek times r, you get the tangential variables from it. So the magnitude of this, right, just to emphasize, the magnitude of this, which we will denote this, is the tangential speed divided by r, like this, yeah. And the magnitude of this guy, right, so the magnitude of this guy, I'm gonna write it the other way around just to, just because this is more popular. So it's the same as writing this and the magnitude of this, so it's more popular to not write things so clumsily, is what do we have? We have omega times, not omega, but the Latin one is the Greek one times r, like that, right? So the magnitude is AT over r, right? Okay, good. So yeah, so that's just the magnitude of it. So that's easy. So if you know the magnitude, and we know the definition, how to define the magnitude of the tangential speed, we know how to define this. This is how much distance per the change in distance, the change in speed per time. There's a change in distance per time. So magnitude is fine. We know how to calculate that. We know how to deal with it. It's the direction that is tricky, because the direction is constantly changing, right? So how do I describe this rotation direction? And here comes the clever part of the creators of these theories, right? So someone came up, let's do this. I want to define an angular velocity vector, so that when I give people the magnitude and direction, they know exactly what I mean, like they know exactly how the motion is rotating, how the object is rotating. And they come up with this idea, is saying, if it rotates this way, let me wrap my right hand around this direction. So it's called the right hand rule. It's just convention, right? So if I wrap my right hand, notice what happens. My thumb is pointing outwards, okay? My thumb is pointing in the positive, let's say XY, let's do XYZ, right? So Z is pointing, the Z axis is pointing out of the board, let's say, right? So this is I, J, K unit vectors like this. So if it's rotating on the XY plane, so if it's rotating on the XY plane, my right hand, if I follow the right hand rule, right, my right hand rule, if I wrap around counterclockwise on the XY plane, my thumb is now pointing in the positive Z hat direction, or positive K hat, or you can call it IJK, sometimes you will call it X hat, Y hat and Z hat. So it's pointing in the positive Z hat direction, like this, or out of the board. So that's going to be my direction of the vector, because vector, like I cannot say the omega sort of just changes all the time. Then sometimes it's pointing in the positive X, that's very complicated, but omega is not changing. Let's say it's going at a constant velocity. I should have a constant magnitude and constant direction. I shouldn't have a constantly changing direction if this is constant, right? So if this is constant, it better have a constant magnitude, which is fair, right? Or the same thing as this. Sorry, this, right? Or D, if it's not constant, this is more correct. But if it's constant, this is similar to this. All right. So the magnitude is fine, right? So if this is constant, but I should also have a constant direction if something has a constant angular velocity. And we define it with the direction of your thumb. All right. So I don't even know how to write it out, but just I'll just call it, the right hand rule. Okay. So it's given, the direction is given by the right hand rule, like this. Okay. So if it's clockwise like this, so now you use your right hand and try to wrap around the motion, right? So now you see your thumbs pointing inwards into the board. So the angular velocity vector, again, it's just a way to define how objects is rotated. All right. So what's the benefit of this? Right. So this guy would have the angular velocity vector pointing into the board. So what's the benefit of defining this? Here's the clever part, right? If I have an object, an irregular object, like, I don't know, a hamburger, right? So I have a hamburger like this, and it's going, and I tell you, this is the, let's say, the center of mass of the hamburger, and it's rotating with this angular velocity vector. Okay, what does that tell me? That immediately tells me something very useful. Okay, so it tells me both the angular speed and the orientation, the direction it's rotating in. What is the speed? Well, the speed is, so if I say this is, let's do it in the magnitude direction ways, right? So it's 5 radians per second. That's the magnitude, and the direction is towards northeast, right? It's better if I have an XY grid, but let's just say northeast for now, right? What it tells me is, okay, so it's rotating with this speed, but the orientation it's rotating at is, point your thumb over here, and it's rotating this way, around this. So the angular velocity vector is a vector that basically describes the axis of rotation. So it's rotating in this plane. So you draw a plane that is perpendicular. So if you have a plane, if I tell you this is the angular velocity, then the object is rotating on a plane that is perpendicular to this vector. Okay. So it's a clever way to immediately tell people how the hamburger is rotating. So what if it's rotating on its axis, like on its vertical axis like this, with the same rotational speed? Then you say, hey, that's not the angular velocity of it anymore. And you go like, that's the angular velocity, right? You see, it's a clever way, right? So now I know not only how fast it is spinning, how many radians per second is it spinning, but I also know which orientation it's spinning, right? So it's spinning, the hamburger is spinning around this way. And what if it's spinning this way? What if it's the other way around? So use your right hand around, right? So this time it's exactly what you expect. If you point the if you point the angular velocity in the different direction, it's rotating in the same plane, right? So you can put this on the table, and it's rotating this on the same plane, but the opposite direction. Okay, takes a little bit while to visualize it, right? So essentially, the rule is use your right hand, point your thumb along the direction of this, and the rest of the finger will tell you how it is rotating. And this is the same idea with acceleration. Is if it starts to speed up or slow down, the angular acceleration vector, right? The magnitude is equivalent to d omega dt. If it's constant, it's roughly this, right? That's fine. So the magnitude of how many radians per second. So if I have an object, let's say I have an apple, and I say, hey, this is the angular velocity vector. So the magnitude, I'll give it in terms of magnitude direction, so geometric way, right? It's, let's say, 5 radians per second squared, all right? And the direction is, this way. I need to define it properly with 3 pieces of information. Technically, this is 3D as well, so I need 6 pieces of information. But so that's why we won't do that rigorously. But let's just get the idea, intuition of it. So if it's pointing this way, what does it tell us? So this is the direction. It tells us that, well, first of all, it's rotating, but which way? It's telling me it's rotating in a plane that is perpendicular, that's normal to this vector. Okay, so I can't, can I? No, can't really draw 3D planes. Yeah, it's as good as I can do. So so put your thumb along the angular vector, right? The angular acceleration vector, and now I know it's rotating this way. Like this, right? So it works better in 3D, right? Okay, so let me try this. If this is the vector pointing that way, so put your thumb around here, that means it's rotating like this. If the angular, you get the white background, there we go. If the angular velocity or angular acceleration is this way, it means it's rotating like this. Just basically use your right hand to tell you which way. If the angular velocity vector is pointing, let's say this way, and just do this, right? So it's going around like this. Okay, how fast? How fast is just the length of this vector. The magnitude of this vector will tell you how fast it's spinning. If I'm talking about angular velocity, angular acceleration, it's how fast is the increase in this direction, right? So it's increasing every second. It's rotating faster and faster in this direction in 5 radians per second. So each second, it's increasing by 5 radians per second of speed, right? So yeah, that takes care of, so now you understand, I can actually define a vector version of this concept of angular speed and angular acceleration. Just to summarize, the magnitude tells you what we understand, the direction tells you the orientation of the rotational motion, okay? All right, so this wraps up everything about rotational kinematics. And the final thing to do is to, so we understand, right? So we have this guy, right? So we know that if we know 3 out of 5, we can find the others. But what causes this motion? And just like with Suvat, right? We know that force is the origin, is the one responsible for all these complications. So something is going to be responsible for the rotational thing, and that's going to be our next topic. We'll see what's going to cause this, and once we know how it causes, we basically have a rotational version, an angular version of Newton's second law. Once we have that, then you can find this and find everything else. That completes the whole story of 3A, of how do things move, how do things spin, how do things rotate, and you will be able to take the foundations, fundamental concepts in this course and apply it to understand a lot of daily phenomena that you can see in the next 2 courses of 3B and 3C. All right, so we'll address that in the last lecture.